I'll hit record. So we've made it through 2 models so far. We keep adding terms and variables and so forth. Let's go to the next part. Now we'll make it a bit more complicated. Now we'll just estimate. I hate saying. I apologize for. Nothing is just. Everything is pretty complicated. But this is one step forward. We're going to estimate a slope for theta that is just that is this factor loading itself here. So following Lisa's multi-level notation, Lisa, would you like to describe why this looks like this?
Yes.
Surprise, by the way.
You're Surprise. On. Yes. No, I got this. I wrote these. I can do this. So in the same way that the expected response can have a random intercept, the expected loading could have what? What could go here?
A random intercept for school?
A
random loading for school? Random slope for school?
A random loading. You could have a U1 for the lambda term. Each school could have a different within-person factor loading. Some items could be more discriminating in different schools. We're not going to do that to you. But because it is theoretically possible, maybe not computationally, I put it in the notation to allow that as a possibility.
By the way, when she says maybe not computationally, that's where my ears perk up. I love a challenge. And I love the ability, I love trying to estimate models that are super complex. Like, maybe that's more of my hobby than everything else on this planet, is like, oh, you didn't get that to estimate? Let me try.
Well, so I could see that in other contexts being a thing. Like, I have a hard time picturing why some items would be more discriminating in some schools in this context. But if this were something like occasions within persons, I could see certain items being more relevant to the trait for some people than other people. So I could see it being random across people more easily than across clusters, but it is theoretically possible, so I allowed the notation to be able to do that.
So let me get your opinion. So to do this, though, we have the same psychometric properties we had before. Remember, this is not your typical multi-level model slope. Right? It is not predicting an observed outcome. It's predicting, or it's not multiplying an observed outcome. It's multiplying a latent variable, something that we did not observe. So therefore, that latent variable, we have to turn off its variance. Unless we use a marker item where we choose one item to not have a slope.
That's next.
But let's ask the question. From model 1 to model 2, we added 3,101 parameters, 3,100 thetas, 1 standard deviation. From model 2 to model 3, how many parameters do we add? In this case, there would be 10 loadings, 1 for each item. We'd be adding 10 loadings, but we would be removing the standard deviation for theta. So here, this is slightly more complex than the previous model. It's not the 3,000 more parameters that we had previous to this. So we would expect this model, if we were estimating it, which I'm not going to in front of you, to go about the same speed in terms of estimation because the number of calculations are roughly the same, or just slightly more. Okay, you want to see the stand code? Again, this will build upon what we just did. Here's our stand code. We have, going to the model, we have our, again, quote-unquote fixed intercept, although nothing is fixed. We have a person theta that now multiplies what I'm calling, where'd it go? There it goes. What I'm calling the within lambda. To represent this is the lambda at the within person level, or the lambda that multiplies just the person theta. Now we haven't gotten a between theta yet, but we're going to come there. We're going to get there, and we're going to have a between lambda. Why not, right? But, of course, just a few more lines of code and a lot more time waiting for Stan to finish. That time, by the way, when Stan runs, it's great goof-off time, right? He's just sort of like, I'm going to read a book, I'm going to go get on social media. No, I'm just kidding. I'm going to sleep. All right, the rest of this line is the same. We still have our item random intercept for school. So this is the same school random intercepts as well, too. And again, we have 62 schools by 10 items, so 620 of those random intercepts per school. Let's see, anything else I need to note? Here, because we've added within lambda, it needs a prior distribution. I'm giving it a multivariate normal distribution, and I'm submitting the lambda, the mean vector and covariance matrix. The mean vector will end up being 0, and the covariance matrix in this case is a bit more informative than you're used to seeing this week. I'm letting the prior standard deviation of lambda be 1. And now the complication happens. Because I'm using a multivariate normal for lambda, I need to ensure that where I start keeps lambda and theta in the direction I want it to be. If you remember the thing I drew on the board where there's actually two modes. We have lambda times theta is one mode is equal to negative lambda times negative theta. Like the algorithm, if it starts on one side or another of 0, it might move towards modes that are reflected about 0. And it looked like it won't converge, but technically they're the same values. It's just they've inverted what lambda and theta are, multiplied both by -1. So this is to keep theta in the right direction as lambda, and then lambda to be positive as well, too. So let's... This is model 3? This is model 3, right? Yes, model 3. For some reason, I expected it to be 4. I'm melting down. Friday, it's like I'm just having meltdown after meltdown Friday. It's like I lost half of my brain. Like I couldn't remember the plug today. Like, anyway.
But our boarding passes are now available.
Oh, we might be able to go home tomorrow. Not that I don't love it here. It is very nice being here. I do. Maybe I prefer less of the workshop and more of the here, but, it's still it's a great place to be. Okay. Let's look at convergence. Ooh, that didn't converge. Something is wrong there. But I'm showing you this result anyway. Bless you. Let's take a look. Let's take a look at our within lambda standard deviations here. These are the culprits. This is what I was telling you about. And actually, I believe you mentioned it to me as well, too. Had I used a log normal prior on these things, we've been a little bit happier, right? Because these terms are effectively inverses of each other, about 0, and that's where the problem lies. So I thought I had fixed this problem, but I didn't. So
conceptually,
what
does it mean?
Conceptually, it means this mean is nothing. It's about, it basically shows you that half of the values are negative and half of positive, or depending on the chain. Some of the chains made theta and lambda go negative, and some of them made theta and lambda go positive.
So that means that in some of the chains, more of theta means you're worse at math, and in some of the chains, more of theta means you're better at math, because theta is imaginary. It doesn't know which way to go.
That's right. That's right. And again, I could fix this by doing making the prior on this strictly positive. Right, making it a log normal prior, making it something like that. I hesitate to do that because as we get to more complicated models, some of those will want to be negative, but maybe I should have. My trick didn't work. I'm surprised because I thought I had fixed it, but I'm sorry.
What does median tell now? And can we use it as a point?
It's a good question. So that's the median of all the chains put together. And I don't know how many were inverted.
Yeah, true.
So if 2 were inverted and if 2 were negative and 2 were positive, then I think we probably could. That's a good way of putting it. But if 1 was inverted and 3 were positive, then we'd need a different quantile or quartile of the distribution to figure out. Okay. Well, we're still building up, so let's just keep going. See. Messy data. Lisa said messy data is cool, right?
It is the world.
It's not cool. But, okay. Let's see here. See, in my previous exam, I must have overwritten this thinking it would run fine, and it didn't. And
you can fix it later.
yeah, I did. because I had, yeah. All right, let's go to model 4. Now, model 4, so model 3 had a lambda for every item, but theta's variance was 1. But remember where we're going. We'd like to explain how much variance of theta is, we want to know how much variance of person theta is explained by adding the predictor variable of free and reduced lunch at the person level. So because of that, if we kept theta's variance at 1, we could add the predictor variable, but we wouldn't be able to quickly identify what theta's variance, how much had been explained. Like other model parameters would start to change. So instead, what we need to do is pick an item where one of these lambdas is equal to 1, and then go back and re-estimate the variance of theta. So this is effectively an equivalent model to the previous one, although I believe we're going to fix the flip on this because we fixed one of these positive. So this should work. So we are going to estimate one, we're going to fix one slope to 1, one loading to 1, and let's take a look at that code. Model 3, you stink. Let's go to 4. Here we go. So model 4, to do that, I just took the very first item and declared it the marker item for that slope. So that means you will not see a within lambda on this item. And then for the remaining items, from item 2 through 10, there is a within lambda. The only difference is here on the first item, I still have to specifically specify the first item for that gamma and the first item for that random intercept. But the remainder will be appropriate. And finally, because within lambda, the index for it starts at 1, like the very first one is the number 1, I have to subtract item minus 1 because this loop starts at 2. So that when we look at our output, within lambda, the very first one refers to item 2, not item 1. Right, so it'll be 2 through 9. It's just one item removed. 1 through 9. So when we look at that. Similar to before, now we have our standard deviation back. This is the same as model 2. The same code for model 2 when it comes to standard deviation of theta and the prior for it as well. Any questions? Okay. Let's grab the results. Let's look at convergence. Ha-ha! It's back. I already sweat profusely when I teach, but when the thing goes wrong, it's like you should. If I had like the little cortisol measure or something like that, it's like off the roof. Anyway, here, which results would you like to look at first? Should we look at the lambdas? Here are our item lambdas. Now, remember, this is item 2 through 10, right? Not 1 through 9. But these are our values of lambdas. They're very converged. Some of them are harder to estimate than others, a little bit standard deviation, but those are high. I don't think anything's really notable about that. The lambda, though, because theta has a standard deviation we're estimating, remember, these aren't on the same metric as when we had constrained theta with the 2PL before, when theta's variance was 1. So theta's variance is being estimated. So let's take a look at that variance. Here, 1.5. So this variance of theta of 1.5, standard deviation of theta of 1.5, thank you. This 1.5 is somewhat arbitrary, right? It doesn't really exist. It's just because we picked item 1 to be the marker item. Had we have picked item 5 or item 10, this will be different. But everything would rescale accordingly. Then, let's take a look at the correlations of those random intercepts. Now, again, I didn't save these from before, but these are, again, the correlation to random intercepts. They're still strong and positive. They may not be as many 0.8s, but it's still roughly the same in the same magnitude. In a quick view of this, and I'm not.
It shouldn't change.
If they're changing in small amounts, but not a whole lot. Also, these are very well converged as well too, so that helps. And if I look at the standard deviation for the item intercepts, these are our random intercept standard deviations. Now these are a little bit more interesting because what theta's variance is, like we didn't have 1.07 before on this, but everything gets rescaled a little bit because of the way that we've estimated theta. So these have changed a bit overall, but that change isn't really meaningful. It's only reflects a change in how we identified the model for theta. Am I missing anything, Lisa?
Okay,
Questions? Who wants to factor analyze some random intercepts now? Yes, I like that. Faking enthusiasm, or better yet, you're still here, so I hope you're not compelled to be here. But anyway, I'm happy. Let's do that. Let's look at the model. Model 5 is where we put it all together. Model 5 is one of our most complex models here.
It's the worst one.
This is the worst. So, Lisa, would you like to walk through the slides since you made this? Or no? It's the hardest. Lisa, come here. I can do it if you'd like. You made this file. You have the notation more. I'm over here in Stanland. I'm doing Koleski. You do the slide.
Yeah. So previously, we just sort of let level 2 just kind of float, right? All the intercepts are just floating up there. They're all correlated. They're hanging out at the bar. They're not having any structure on them. Now we're bringing them into the story. So the within level looks the same in that we have a loading that is item specific. It is fixed, meaning it does not vary across clusters. And theta's variance at the within level is being estimated. Let's see, that means we need a marker, which is right here, right?
The one right before it.
Oh, this one, yep. So wait.
Yes, the first item.
Yeah, okay, there it is, the one. Sorry. What I'm looking at is the little tiny number 1 right there, meaning the first item for the within level theta is fixed to 1 for identification so that we can estimate the within level theta variance. Now at level 2, we have, this is from before, that's like the fixed intercept. Here's the random intercept that was just hanging out before, but now this is random intercept left over because we've introduced school theta into the story. So we have in keeping with the OO, I've called this O1 in terms of the subscripts. Each item gets a different between level lambda that is a multiplier slope for between level theta, whose variance is going to be estimated, it looks like,
yes,
right here. And let's see, did I forget anything?
No, the marker for it is the 10th
yes.
item. Although that's a bit of a typo. It should be that number right there. 0. Lambda 01.
Okay. It's
funny, I looked this over before and didn't see it.
Yeah, you
Of
can't
course, when
see
I'm
it until
teaching,
you're in front of people.
Trying to give you the
when
fine
find it.
detail. Yeah.
Yeah, this is a bit of a nightmare. So can anyone guess why we decided to, based on the title of this model, level-specific loadings for each, why we picked a different item for the marker at the between level than the within level? Let me ask it a different way. Is 1 equal to 1? Usually. Yes, right? So if we pick the same...
It's Friday.
I know, that's why I went with that. Is 1 equal to 1?
You asked me that at
Yes.
11 p.m. tonight, and I went not answered that correctly.
So we made the same item the marker, it's actually a constraint in that case. And we didn't want to have the... see? Is 1 equal to 1? Yes, it is. So we didn't want that. So we deliberately picked a different item to be the marker. That way it really is a separate theta on each level in this model as like the biggest, scariest thing. How's that?
Well done. Well done? Yes, question.
But then aren't they on a different scale?
Yeah,
Yes.
Then you don't really need to compare them, or we don't?
That's right. In fact, it's difficult to understand what the relationship between the two represents.
Not the same thing.
Because if you think so, interestingly, like there's very few examples of this because basically, if you think of psychometrics, where you have two traits being measured by items, right? Seldom do you find those two traits on all the items all the time. It's not identified, right? You have to somehow turn one off, or you have to have other items where that trait isn't measured, right? We have two traits on the same items, but they're at different levels. Because they're measuring the same items, they're measuring something that's similar, like from a conceptual point of view. Is it exactly the same? No. And that's where I have this thought experiment. Half of my brain wants to say, yeah, they're the same thing, but it's harder to measure at different levels. Half of my brain says they're not, but what we can say is that the within theta is not a deviation from the school mean in this case, because if that other thing is not measured the same, it will not be the same metric as the within theta. So
Yeah, different concepts and different scales. They're completely different.
So this is like the crazy model, right? This is really complicated for measurement. But, I mean, there are open questions in my mind that I don't think are answerable, or that are answered, or maybe you may know better than I do. For instance, if my goal, I mentioned the goal of this assessment was to measure the schools. If my goal to measure the schools was there, and this model fits better than the one before it, and I'm not concerned about person theta, is this school theta the best estimate of the school then, right? From a measurement perspective, would that represent it? I don't know the answer to that. I'd like to say it is, but I don't know.
This would also be the model, by the way, that in the ergodicity, have you heard that term before? The idea that between and within aren't going to map onto each other. Someone who believes that between person variation and covariation is not an acceptable proxy for within person information would be totes fine with this, because it's completely separate in that case.
Any other questions? To the code. Close those. Model 5. Okay, here we go. What do we do now? That last item conveniently works nicely in stand 2, because the last item here is the marker for within and between. So let's talk about what happens. The first item is our marker item for the within level, within theta. So what you see is a fixed intercept gamma, the person theta that's not multiplying any lambda, right? So that's the marker, it's set equal to 1 there. And then we have a school theta, which is new, multiplying a between lambda. And then we have what's left over, the school random intercept. Right? So if you actually want to think about it, if we were talking in class Tuesday about this model, that's what we called confirmatory factor analysis. It's just what confirmatory factor analysis are those random intercepts themselves for each school. And that's why the item random intercept still stays. For item 2 through 9, items 2 through 9, we have both the within lambda and the between lambda. And I will note within lambda again goes, number 1 of within lambda represents item 2's value, whereas number 1 of between lambda represents item 1's value, because I had different markers on each. And then finally, for the last item, we have a within lambda, but no between lambda. Okay. So now here's the big question. Actually, let's just do this. School theta has a normal distribution, where we estimate its standard deviation. And just like person theta, the standard deviation here will follow a similar log normal prior, but I'm going to allow for different hyperparameters for it, just in case I need to change values or otherwise have different beliefs about school versus person. Let's see. So how many new parameters am I adding in this model? You want help with that one? Should I just tell you?
Count them up.
All right. So we have school theta. There's 62 schools, so there's 62 new thetas. and we have between lambda, of which we have 9. 1 for the first 9 items, and then the last one's set. So that's now 71. And then finally, a school theta standard deviation. So 72 new parameters. So quite a few new parameters with it. All right. You want to begin this? See the results? Okay. This model is the most complicated measurement model of the week.
That's it.
From here, we will reduce the complexity of the measurement model, but then we'll add in the predictor. Okay? I know. Trade-off. Okay, let's see how convergence works. What? It converged? Yes. Excited. All right. Let's take a look at the school. Let's take a look at the standard deviations first. So what is this telling us here? Whatever school theta represents, some type of school mathematics ability, its standard deviation is 0.875. Whatever person theta represents, it's a person's mathematics ability after controlling for the mathematics ability of the school. However, they're not exactly the same number. That is 0.5, 1.5. Again, this was what it was before. Yet again, reinforcing, I think, the belief that these are between. The slopes are between.
Yeah, the person theta is how much smarter you are than everyone else in your school.
So then let's take a look at our factor loadings. We'll have 18 of these. So here are the top ones. This is item 2 through item 10. You just have to add a number to each of the indexes for within lambda. And then we have item 1 through item 9 for between. And here, they are very similar in magnitude. If you think about it, they may not be the saying like almost like if we were to do a little bit of a scatter plot, I think we'd see a fairly high correlation, meaning items are measuring the people similar to items are measuring the school, but they're not on the same scale, and that's because the school variance was smaller than the person variance. What else can I add about that? These are in the multi-level model. Here's the debate that Lisa was talking about. When we see a slope here, this is a level 2 slope. Remember yesterday, the smushing conversation is this. This is not, level 1 is not smushed. Level 2, is it between or is it contextual? That, yet again, who knows? I can't move my wrist, but, there.
I think it's between.
Between. We have this, I think we both settled on this is a between slope itself. But it's.
You correlated the thetas in the posterior. You want to tell me about that? And it wasn't correlated.
That's right. I looked at, so how we arrived at this is I took the EAP estimates of our person thetas and their corresponding EAP estimates of their school theta, right? So I made a 3,100 observation by 2 column matrix, estimated the correlation, it was close to 0. It was like 0.02 or 0.01. So remember with the slide that Lisa showed when she took the cluster mean centering approach, and she showed sort of the numbers, there was no correlation between the within person value and the between person value when you cluster mean center.
Between and within cluster.
Between and within cluster. Here, there is no correlation between theta and within theta as well. Should we look at our school thetas?
Sure.
We looked at school 62 before because it was the last on our list and it had high random intercept values. That makes me think its theta will be somewhat large too. So why don't we do that too? Actually, any other questions about lambdas before I move off of those? Nah. All right, school theta. Nope. There we go.
Yep, you're smart.
So here are our school thetas. The last one, 0.726, it's fairly high. This is the amount of variation around school theta. So here's a question for you. Would you expect us to have more or less reliability for measuring the school than we have for measuring the person? Let's think of it this way. How many pieces of data do we have to measure a person's data? 10, right? Or 10 items. How many pieces of data do we have to measure a school's data? 10 items by 50 students. So I would expect, although I haven't looked at it, so I always love these things where I do things on the fly and I crash.
Yeah, this isn't working.
But let's take a look. I would imagine, I will conjecture, that standard deviation, if I show you the person theta, they will be much larger. Look at the range of these standard deviations. There's not a lot of variation in standard deviation. I think that's probably because we're measuring the school theta. We have much more information for school theta than we have for person theta. But let's take a look. And the answer, yes. There we have it. These are an order of magnitude higher, almost twice as big posterior standard deviations for the person theta than what we have for the school theta. This actually is one of the debates I have had. I don't know about me, but some of my colleagues have mentioned about our educational system in our country. We force students to get assessed at the end of the year because we want to talk about their school, but we force all of them to be assessed. And we force all of them to be assessed with very long assessments. I mean, it's taking out almost a month and a half of their school time just to prepare and take this silly assessment. And if you think about it, we probably could get away with taking a sample of students from a school to assess their school better, right? But then we burden only a few students. And then everybody also wants to take the student values and say, oh, this is important. I want to see how my student's doing. But usually the assessments are such high level that you couldn't really tell much about how well they're doing. It doesn't really correlate with many things. Okay. Anything else about this model that you'd like to see? Do I dare? Do I have this? Let's take a look at leave one out. All these models. Within person, between school. What did I call this one? I shouldn't have done that. I should have just called them model 2, 3, 4, whatever. So this last model we ran was within person, between school. The one prior to this was where we did not have, what was 4 again? We did not have our school theta, right? Turns out, from a leave one out perspective, the model prior to this
is bigger better?
Yeah, 0 is better. This one, the one model prior to this, is slightly worse, but look at the standard error of the difference. So it's hard to distinguish between the two. And then the model where the slopes were all backwards is also similar, but these two models were actually roughly equivalent right here. But, so whether or not we have a theta at the school level is questionable in this approach from this point of view. Like if we're doing model, like relative model fit in this perspective. What do you think, Lisa? Anything to add?
This blue thing is suspect.
Yeah, it's kind of sus. Any questions about what we're doing here? Is the why answered? Do you want to know why? So now we have a school theta. We could predict it. We have a person theta. We could predict it. We have all the ingredients in place to do what we did at the end of yesterday by predicting between and within score based on our Fourier reduced lunch. Yes?
But based on the LLO, shouldn't I take the first model?
Yeah, actually, so what I would say is it is questionable as to which model seems to fit better based on model parsimony between these three right here. And the reason why I say that is if I look at the difference, if I look at the standard error of the difference, really it could be the case that any of these three fit better. But the one before this, before we put in the slopes for person, right? This was the one parameter person model with the school random intercepts. That fits way worse. And when we left person out, that one's, forget that one altogether. So based on this, it's questionable whether we should have a school theta. But we're going to simplify this. Well, no?
No, I disagree with that.
No?
No, so the model where the random intercepts were just floating and all correlated is as good as it gets, right? That's the saturated model in terms of fit.
True.
So between school theta is trying to reproduce.
But this is not absolute, this is relative. This is relative with the penalty for number of parameters.
But I'm saying even relative, it's like that letting all the random intercepts just correlate should be as good as you can do at level 2.
True. And we still have them here.
Yeah.
But the fit is improving as we're adding more. The question is it worth the number of parameters that we're adding as we improve it? That's what this is trying to do. All right, let's look at model 6. What we're going to do now is take a little bit of a deviation because I don't know that school theta is really what I think it is. So instead, what we're going to do is constrain each of the loadings to be equal across the between and the within school level. So all those between loadings are going to be equal to the within loadings, which also means that we can set the marker item, the same marker item, to be 1. So we're going to set item number 1 to be the marker item for both between and within. You want to add?
No, I got it right that time.
Yeah. So again, this is actually a reduction in complexity of the model. We're removing 9 loadings from the between level to set them equal to each other at between within, in the between level and within level. Questions on this? All right, going to the code. You can probably expect that this will be slightly simpler.
So this is weak measurement and variance, by the way, in terms of the terminology.
So here, our lambda for each item is multiplying the sum of school theta plus person theta. So this is where you really can see the person theta being a change or a person's deviation from their school mean. Right? This is one where we would say, if we wanted to come up with what a person's theta is, like from a 2PL perspective, it should be the sum of the person theta and the school theta, right? Putting it back together. Okay? Nothing else really is different from this. All the other code is basically the same. So I'm just going to flip to the results. Oh, don't do that.
No.
Dang it. Stop. Come on, Templin. All right, here we go. Let's take a look at convergence. That we are close to where that's the last time we'll find convergence, by the way. So let's take a look at, what do we want to do first here? Take a look at our lambda parameters real quick. These are our estimated factor loadings or discriminations. Again, somewhat of the same magnitude, but remember this is item 2 through item 10, not item 1 through item 9. Now let's look at standard deviation. Here we go. So we have person standard deviation of 1.47, school standard deviation of 0.739. Now that school standard deviation has changed, but 2 things have changed about this. Number 1, marker item is different. And number 2, the loadings are constrained to be equal across levels.
Did you do an ICC?
Did not.
Can we make one real quick? Out of just the numbers?
Yeah, would you like to see an ICC for each of these? We can do that.
Just use the point estimate.
So 0.739 is the between, right? Divided by 0.739 plus 1.47 squared.
Oh, 20%.
So what's this telling us, Lisa?
So yesterday, do you remember how much variance there was in the sum score at the school level? About 16%. We got 20%. So school is a little more reliable, maybe, I guess. But it's pretty close, which I think lends confidence that we might know what we're talking about, even though these thetas are imaginary. right? It does correspond to what you would get if you did the simple version with the sum score to some extent.
The other thing we have here are the item random intercept standard deviations. And this is, remember, what's left over after explaining the school theta, right? The U for each one of those. And I wanted to note this. We haven't been talking about this, but we could also form a random intercept or an ICC per item, right, with this?
Yeah,
It's
but
a little
it's like
weird.
leftover.
Yeah.
The ICC of the leftover is a little weird.
But you'll see these are smaller than what I had shown in the first part of class, and that's because now the random intercept is left over after accounting for the school theta. Right, if we go back to our model here, that U term now has this line for the random intercept for school now has a component that is absorbing some of that variation, explaining some of it. Although it's weird to say a latent variable explains it, but that's what's happening. It's shrinking. Okay, questions on this? Nah. So let's try one more simpler. Actually, let's do this. Although it's a bit suspect, let's try it anyway. Which model is preferred? Let's see. In our output, we've got a set of candidate models that are fitting about the same. This one, where we simplified it, this is the simplified version. This is the one before it. Sorry, this is our simplified model here. This is the model without the factor loadings at the school. This is the model with different factor loadings between and within. So it's roughly equal in comparative model fit. But let's go one step further. Let's do what you say people do,
Yeah.
because they can't get this thing to run usually, right?
Take it away.
We're going to, yes, question.
If you have these models that fit kind of similar,
Mm-hmm.
would you report all of them, or would you
Jeez.
report just one, or how would you decide?
I think if this is a paper where we're establishing a measurement model at both levels, I think we would describe each of the model fit, each of the models that we had estimated, and yes, how comparative they were. At some point, we would probably I think most papers, people would make a decision and try to use that evidence to support or contradict the opinion. Additionally, what I'm not showing here is absolute fit to the data as well. We would also have to show that each of these models has a good absolute fit. But that is, Bayesian, that gets a little hard as well too. So long story short, most of the times I've done this or seen this happen, we do list comparative models, but we say we actually are going to describe this one because we believe it's the case, leaving open the possibility that in a different sample or a different set of data it would be different.
And would you also report the ones that were really not so good, or that's not?
I think I would probably describe them as to sort of where we built. So this whole step-by-step process that we're doing here, I think we would probably describe them from it if we had space. We're running out of room pretty quickly. But in text, I might put a table in saying there was a set of models, maybe a brief description of what each is, and then highlight the ones that are within the range of what seems to fit best, and then pick the one from there. Hope that helps a little bit. You're welcome. And I will add, whatever I tell you is subject to the opinions of reviewer 2 in the journal. So that might always change as well too. So, yes.
If we, for example, see a suspicion pattern of the random intercept correlation, could we, I don't know, could we argue that some kind of little item dependency we need to fix?
Actually, I forgot to mention that. So when we put the school theta in, I removed the correlation among random intercepts. So there is no residual correlation anymore from it. I should have mentioned that. I didn't. I apologize. Here, let's see, that was in model 5, right here. This term, U, now, I should have mentioned this, just follows univariate normal and thought to be independent.
Could we test these?
I'm trying to think here. Is that it's not identified to estimate the correlation after your control
But
for
you
the
could
trick.
put a few in if you need
You
to.
you could you could put a few. Yeah, I guess there's a way that you could sort of put in like residual correlations. You can't put all of them in, but you could put one or two in. That actually would be a little bit more complicated in the Bayes estimation, but you could do that.
But then it's like the regularized SEM approach. So we see.
That's right. Yeah. So, but yeah, I think all options might be on the table, but I'm not sure.
I can see how it would work in the picture.
Yes. Right. Yeah. You have you just have a residual like it'd be like a residual covariance in a measurement model like a CFA. But and that's the other part. I mean, Lisa was mentioning fit to level 2. In theory, we could have taken the residual covariance matrix from the model prior to correlation matrix from the model without theta at school level, and then the one with, I guess we don't even have that there. I guess we could come up with what the model implied version of it would be and see how well it fits to it. So we could come up with a local version of fit for it.
Sure.
Yeah. Maybe this is a 2-semester class. Sorry. All right, so let's do model 7 with the missing random intercept variance.
Scalar invariance.
Scalar invariance. The stand code for this, I should note, is, as you would expect, very similar. The only difference, no random intercept there. This is a vastly simpler model. We with a random we still had 62 schools by 10 random intercepts in the previous model, so we're taking out 620 parameters to do this, plus their standard deviations, so actually 630 parameters. So we'll load this. I would expect the model to converge. Ooh.
It's under 1.1.
Yeah, it depends on who you like to talk to. And here are some results. Again, these values are relatively unchanged. I guess this one's a little bit smaller than the last time.
Person theta is throwing up. That's your R hat.
Yeah, that one right there. And then if we wanted to compare model fit, this one is no random intercept. Its model fit is much worse than the ones we ran prior to it in terms of leave one out. So maybe not the best idea to remove the random, to shut off the random intercepts and their variances.
Yes. What does that mean conceptually?
It means there's no variation in intercept at all. Once you account for the school theta.
Yeah, theta between school theta explains all the random intercept variance perfectly, or that there's no cluster specific deviations in the expected response.
When does that happen? Not sure. It's not likely to happen. All right. Now comes what we're waiting for. The reason we did all this week. We would like to know how well free and reduced lunch predicts mathematics ability at the school level and at the person level. So we're going to take model 6, which was the model that has the random intercept variances, but also has the school thetas, where the loadings are constrained to be equal at the between school and within person level.
Within school.
Within school, between and within. Okay? Now, because we were trying to do the ideal, right? Remember we talked about less than ideal yesterday? Yesterday was less than ideal, maybe not wrong, but less than ideal. This is trying to be the ideal, attempting to give us the ideal. What that means is we're actually going to use free and reduced lunch in a multi-level model as well too. So now we've got the multi-level measurement model for all the 10 items where students are nested in schools, and we have free and reduced lunch variable, observed variable, in a 2-level model where students are nested within schools as well. So what we're going to do with that free and reduced lunch level 1 model is come up with a random intercept for school. And then for our multi-level model, we have our item responses here. We take our person theta and we multiply it by some type of slope that has a within school loading. And now our person trait theta, we are going to predict based on that person's free or reduced lunch with some type of placeholder right here that has a fixed slope. Okay? So now we're describing a person's deviation from their, how much a person deviates from their school mean as a function of their free and reduced lunch status as observed. Would you say that any differently?
No.
Okay. Yeah, I always, when I get to the multi-level part, I'm like, oh gosh, the expert's here. She's going to be, so here. Second, the between school. Now let's take a look at this responses intercept here. That is a random intercept where we have a fixed term, a school level theta with between school or school level loading, and a random intercept. And here we are going to then predict the school level theta with the random intercept for free and reduced lunch on the logit scale. Right? So what this represents is the impact of 1 unit change in free and reduced lunch in logits per the change in a school theta per 1 unit change in logits of the free and reduced lunch random intercept. So whether or not a school's logit of the proportion of students on free and reduced lunch predicts a school's level of ability on the trait. Now, let's talk the random terms, right? The within school trait, each person's theta has a residual term, if you want to call it that. We would just call that theta has some type of variance, within school variance. This is now a residual variance because we're predicting theta with the observed free and reduced lunch. Right? Then, for the school itself, we have we have a free and reduced lunch residual variance that follows this normal distribution here. That variance is not explained. Right. This is a predictor variable that it just varies, but we aren't describing why it varies. We have our random intercept variance again. This term right here has a variance per item. That's what's left over in the item intercept once explaining for theta. And finally, the school theta has a residual term that has a residual variance tau squared. So if we wanted to describe a pseudo R squared for what school variance is once we predict it with the school level free and reduced lunch random intercept, we would look at this term in comparison, the term with the model where we didn't have the random intercept in, the school variance from model 6. What have I left out? In this model again, all of the marker item is number 1. All of the loadings are the same. What is it?
No one there.
O1 here. This should be a lambda, right?
No.
Oh, that's right. Gamma's.
The lambda needs an O1 in front of it.
Yeah.
There you go. In common.
All right, so this is the multi-level measurement model that matches the last model we ran yesterday. Right? Where we had, remember the last model we had a multivariate multi-level model where we had the free and reduced lunch on one side predicting the sum score at both the school level and person level. Right? This is doing the same. However, now instead of predicting the sum score, we're predicting the school theta and the person theta. Right? At each level. What are you laughing at?
I'm just laughing at this. This is nuts, right?
So I would say, so in the ivory tower of academics, like in the theoretical world in my little tiny brain, this is the ideal. Right? I said yesterday was somewhat less than the ideal. Like this is the ideal. Like we're accounting for unreliability, both at the lack of reliability, both at the random intercept for the free and reduced lunch at the school. We also have the unreliability or lack of reliability potentially for each of the traits, student, school. This is putting it all together in the way that's like we've worked for 125 years to get to, right? So let's take a look at what happens. Shall we? Okay. Who's ready to be disappointed? Let's go to the R hat. I need a horn. Womp, womp. What? Okay, so I can't tell you the number of times I have waited, a number of hours of my life I've waited and worked with Stan to try to get this thing to work. But I want to dive into it a little bit more, even though it's an unconverged result.
We know what.
We have a feeling as to what happens. And we started to see this a little bit yesterday when variances get close to 0. And I'm probably using the wrong prior. That's the next thing I'm going to try. I've tried like 18 other ways of looking at it. But one of the things I wanted to show you was, let's see. Let's do just let's take a look at the standard deviation. So this is the residual standard deviation for person in school after accounting for induced lunch. I realized I didn't show you this in Stan. Should I show you the Stan code first? Probably should show that. It's a little bit more complicated. Here.
We do have an hour left, so you can take your time with it.
Well, I know, but everybody looks like they're checked. No. Let's see it. Let's see the code. Everybody's hungry. It's lunchtime. Let's see here. The measurement model is largely the same. Now where the difference is we have a free and reduced lunch model. So we have a free and reduced lunch variable in. And now the person theta, basically when we predict the person theta, we're actually predicting we add that prediction to its mean. However, there's no intercept to it to identify the person theta. Now for the school theta, the same thing happens. We take the free and reduced lunch slope here. Actually, I've tried, this is the last iteration I tried. It did have the random intercept in it before, and we're multiplying it by a free and reduced lunch slope. So rather than dwelling too much on this code, I want to show what happened. Let's take a look at this. Let's take a look at the school theta standard deviation, shall we? Have you ever seen an estimate that small of standard deviation? So what I believe is happening here is because remember yesterday in the observed variable, we explained how much variation in school? Was it 82% of the variance in the school? Right? So that means the school variance goes very, very small. Here, that number is very small. Now the person variance is actually larger, which is a little bit weird. And that, what's that?
That's a consequence of rescaling.
Yeah. Oh, that's right. Rescaling.
Yeah, we can talk about that for a minute.
Yeah. You want to talk about it?
Maybe. You can finish your thought.
But that number is super tiny. And this is that setup where my current belief is I've got to go back and study what Andrew Gelman talks about when it comes to variances and some of the weird priors he's used, like I'm blanking on it, a Cauchy distribution or so forth, to try to think about, because when the variance reaches a boundary, like the whole thing starts to fall apart. Moreover, this is the trace line. Oh, no, I didn't do that. Do I have a trace? I don't have a trace. I'll leave that right now. But the bigger picture is what's happening is our school trait variance is really the suspect here. I don't believe that we're accounting for 100% of the school variance. I think what's happening is it's close to 0, but that's causing the model itself to go crazy. And I've tried remedies of simplifying the model. I tried this with each of the other previous versions of the models where I shut off like the random intercepts, no change. When I allowed differences in the factor loadings in different levels, no change. The same thing. This is always close to 0 here. Oh, and this takes about 24 hours to run right now. I've run longer chains. I've done all sorts of things. No luck. So I have a Model 9 that I'll show you in just a bit, but let's do rescaling. Let's talk about it.
Oh, just one thing to keep in mind. So when you're dealing with generalized models, what is the residual variance if I'm using a logit? We learned this yesterday.
3.29.
3.29. What if I have a super duper good model that explains a lot of variance? What's the residual variance?
3.29.
Right. So the problem is that whenever you add predictors that explain what would have been level 1, everything changes scales to make it so that what's left over is still 3.29. And I have an analogy for this, if I can spend a second on this.
Please take as much time as you need.
So, yeah, move away from Stan for just like 30 seconds here. There's a department store in the States that I shop at all the time, and it's called Kohl's. And it's one of those stores where everything is on sale always to some extent, and then they mail you coupons, and when you go there, they give you cash to spend next time. So basically, if you pay full price at Kohl's, you are doing it wrong. Okay, that's just not a possibility. So let's say that you're the manager of Kohl's, and you have an item that you need to sell for, say, $25 to break even. So what do? You put the price tag at $50 and you say, it's half off. And then you get people to buy it, and then you have a whole bunch left, and it's like, well, I can't reduce the price. What can I do? Oh, I'm going to change the original price to $100, and now it's 75% off. This is essentially the same type of rescaling that's happening. If you think about the original price of the item as the total variance of what the model predicts plus the 3.29, every time that you explain the variance in order for the leftover to stay 3.29, the overall total original price had to have increased. So that's why when you have models with different predictors and you try to compare the scales of the coefficients, they're not on the same scale because they're both relative to an original full price that is a moving target because the residual sale price has to stay the same. How's that? And if you'd like to shop at Kohl's, I'd be happy to talk more about that.
I was also going to show you the slope variable real quick. These are the slopes predicting each of these, right? So each of the person theta slope, so a person's, again, we can't really use this because there's no convergence. However, we would, if we were to pretend this were converged, we'd say for every, this is the difference in school theta mean for students who are on free and reduced lunch. Or another way of putting it, a person who's on free and reduced lunch is about 1.18 units of theta below their school mean. Below a person who is not on school and free and reduced lunch. And similarly, we see a similar effect here that for every 1 unit increase in the logit of a school's random intercept of the proportion of students on free and reduced lunch, the school theta decreases by about 0.28. So that's we're seeing the same effects in the same direction, but we're getting this weirdness in the analysis.
The scale is impossible.
So, again, I've tried a lot of things, and then, was it Wednesday night, I think Lisa said, well, why don't you just estimate the covariance? So, what we did instead now, at level 2, and I don't have a notation for this, but instead of using the prediction of the level 2 theta by the random intercept, instead I created, where'd it go? Did you see it? A school random intercept. 2 school random intercepts, basically. One representing the theta, and one representing the random intercept from the logit model of free and reduced lunch. So rather than one predicting the other, I'm going to have a joint bivariate normal distribution put on there. And why I'm doing that is that the bivariate normal, if you think about, are you familiar with conditional normal distributions? I don't know if you get a covariance matrix. So both of these things were thought to be normal. They don't exist, right? They're latent terms. And before I phrased one as a predictor and one as an outcome. But if both of them were normal, we could have used the bivariate normal and estimated the full covariance matrix between them. And then there is a nice, when you have a bivariate normal distribution, when you say I want to predict one of these variables from the other, there's a nice easy formula to go and get the slope for the prediction and the residual variance for what that happens to be. It's like a conditional, if you look up conditional normal, you'll see all these formulas and so forth. So this is what I tried to estimate. Interestingly, I have numbers, but there's a different story to this, talking a little bit more about Stan's sampling. So rather than go deep into this, again, you can see, of course, I have a Cholesky here. That shows up again. But interestingly, when I ran this, it didn't work at first also. So I thought, let me just see the entire Markov chain. Let me stop warming up. This is a terrible idea. Don't do this, right? This was me trying to figure out and troubleshoot, like, where is it going nuts? So I ran 25 iterations of warm-up, right? By the way, I had also, in some of the other versions of this, I had changed some of the technical parameters in Stan, sort of the adaptation level, the tree depth, the ways that it sort of tries to pick new parameters. Because I actually think when it starts to get that weird boundary somewhere, it's causing all sorts of problems. But here, should be here. I wanted to show you this. Oh, no. That is the wrong one. Got two here. Take a look at my R hats. With 25 iterations of warm-up, I have really good R hats. Right? What is going on? And then, but one of my school thetas is at a constant that's super huge, which is also weird.
It's all scientific notation.
Yeah, that's because this constant right here is really not really a number. I ran this model prior to this, and it did work out, but now it's not. I ran this last night thinking it would work for us, and then of course this is what ended up happening as well. So the ideal, I'm going to try to get to here, the lesson of the week, 125 years of psychometrics theories. I guess it's less than 125, about 120 years of psychometrics and theories, going back to like Spearman, like the G paper, to get to this part, and I can't get it to converge for you. So, deeply disappointing to me, but I'm still going to continue to work on it. And if I do solve it, and it may be a year from now, all those email addresses that I'll go to the email addresses of all of you with the BCC, and I will add it. I will send you an updated Dropbox folder that you can download and see it too. But this is what I have for you. So, not my ideal for how to teach. Realistically, most of my anxiety this week about teaching this is showing you this right now. But if you have suggestions for how to make it work, I'll take them. Question?
The thing is, this will probably happen to our data and models as well.
Lisa, you said you've seen this happen in practice. You've done it more than me.
Not Bayesian. No,
But in non-Bayesian.
Yeah, no, in all these models, there's always some footnote where they say it didn't converge or it was non-positive definite, so we constrained this, shut off this, did this. Okay, here's our results. I don't think it ever works properly unless it's simulated data.
And that was either, like you said, when M+ does this, that does limited information.
I think if you say it's categorical, I think so. But most of the applications I've seen are taking ordinal items and treating them as if they're continuous because that's a lot easier. Yeah,
this is the strict IRT version of it. that's giving us problems. Now, I will note the measurement part itself
This one.
did work. And I could do the less than ideal plausible value analysis on those thetas as if, so it's like a secondary analysis to try to analyze that data, which would be closer to ideal. But because it's a joint model, this might actually change some of the measurement model parameters as well too. Hopefully not, but it
Yeah,
might.
I don't like that.
So, but the secondary analysis?
No, I don't like the idea that predicting it should change the measurement model. I feel like that should be its own thing that stands alone.
So this is a big part of
I
what
know
we
that
do.
does happen.
Oh yeah, it happens significantly, and this is what is the option in M plus for? It's like the 3-stage, or there's a 2-stage. Well, actually, latent class analysis, right? 3-step latent class analysis to make sure that when you predict the proportion of people in each class, it's done on a secondary analysis, so it doesn't change the rest of the classification, right? So it's the same premise here, just with not a latent class model. Questions? Yes.
Thing is, so maybe I missed that, or I'm not sure, but is there any specific reason that we do the constraint scale identification on the this marker item level, but not rather the variance of the thetas?
I mean,
My question is, to be more clear, can't we just fix the variance of the latent traits and estimate all lambdas?
we could, and that's an equivalent model to what we're trying to do. The difference would be when we predict the latent trait with another outcome. Here, let's go here. When this happens, when we put in a prediction function, we would expect this variance to decrease. So if we have the variance of 1 here, it will not decrease. But so we will be able to get an estimate of the slope for the prediction, and that might actually be sufficient. But we wouldn't be able to get an estimate of what a pseudo R squared might be, of how much variance is explained, easily at least.
The other part of it is that there's not just one theta variance to fix, but 2. And if you have a model where the loadings are constrained, meaning you can think of it as like 2 parts of the same variable, what are you enforcing if you fix both types of theta variance to 1? An ICC of 0.5. And if that's not what it is, then that would cause problems.
Going a step further, thank you. I might try that actually.
One of them could go.
But you could fix the school level variance to 1, but leave the person level variance as estimated, perhaps. And at that point, maybe, but then you still have that marker item on the person, but maybe not on the school, and that changes everything. You'd actually, I don't know.
You'd have to tie them together, but not constrain them to a number.
Yeah.
That's what it is.
There's another. I mean, I guess there's other ways I could test my hypothesis that things are a boundary, like the boundary is causing Stan to just not function well. But if I look at the variance parameter here, I have a lower bound of 0 here, which is right on the margin. I bet if I change that to something above 0. I know that's somewhat dissatisfying, but I mean, when do we want a variance to be 0 anyway, right? So if we made that 0.05 or 0.01, 0.02, that might be enough to provide, to test my hypothesis that I actually think it's the momentum parameter that starts to have problems as you get toward the boundary. It's sort of like a black hole almost that it doesn't, I mentioned this, your poster yesterday was something about black holes or something like that, I think, but it sort of gets drawn in and it can't get back out. And this is in the old days when all I had was Metropolis Hastings, I had this problem also with estimating terms where 0 was a lower bound. And a colleague and I ended up trying to, with a proposal distribution, something called the moving window that sort of moved it away to allow it to sample further up to try to get it from sticking on the black hole. So I think this is more of like a technical issue. So my options are switch to Cauchy prior, and then perhaps change the lower bound a little bit. I was trying to fix it with the adaptation and sort of the tree depth, but it was not working either. Anyway.
But it was funny to see that large number. I'm not sure, but can't you use some initial starting value?
Oh, I've tried that too. Yeah, I tried that too. I was like, oh, the variance is 10. and interestingly, so if I run this model where I allow a normal, so I also thought, okay, I'm not doing enough warm up. Because sometimes, if you're far enough away from the posterior, the center part of the posterior, it takes a while to figure out. So I ran an extra long warm up, and then I looked at sort of the warm up values as it had gone along, and all the parameters don't move at all. It's almost as if where they start is where they end, which is indicating to me, again, it's just something with the sampling regime itself, like the variance of the sampler. And actually, I can go a step further. For those of you who are into STAN, CMD STAN-R has a diagnostic set of diagnostic parameters that come with it if you use the sampler diagnostics itself. And so here, nope, it did not save, I don't think. Let me see if I have it. But basically, at the beginning of it, no, I guess I didn't save it. The beginning of it, or actually in the diagnostic value, it was accepting every value. So it's accepting every value, but it's infinitesimally small variance, which makes me think this is a technical issue with STAN that I haven't solved yet. So anyway, thank you for the question. I saw a question over here. Yes?
I think it's a new question, but
Great.
it's quite, I don't know, in my data I don't expect to explain so much variance.
Good.
Good for you then.
I mean, would be nice, but I think, well, this won't be the problem. So, I don't know, I would love to have a feeling of how achievable it is to make such a model converge. Because with limited skill, when to stop?
I think you have a lot. If you're working in JAGs, you have the ability to make this model converge in STAN or in JAGs potentially, if you're familiar with it. So it sounds like you have a lot of the skill. The skill won't be the issue. The issue, and further, if I could remind us, like the model that didn't have the predictor, and the most complicated model, where we estimated all the other converged with the maximum R hat of like 1.03. So what that tells me is it is possible to get this to work. It's when we added the predictor that everything started to break. And so it could be the case that if you're not explaining, I mean, my conjecture is that there's something about the boundary. If that's true, and that's a big if, then if you're not close to the boundary, I suspect it should work with what you have. If it's not true, then maybe it wouldn't be feasible. But I do think this is feasible to run. I think we're right there because this model works. And technically, when we're adding the random intercept, if I didn't add the predictor, I ran that test. I tested the random intercept by itself with no prediction of theta. So basically a separate model with just the random intercept for free and reduced lunch. That one worked. It was when the prediction happened that caused this to stop. So I do think you're close. I think you might be able to do it. But then again,
So with bad predictors, we don't have to run.
That's right. Well, or better yet, if with really good predictors. Because this is one where we know it's highly related, at least. So, thank you for the question. Yeah, that does bring up a good question. I mean, what is practical and what is like the ideal? And that's where I was saying yesterday. Is this wrong or less than ideal? Well, this result is wrong because we can't use a non-converged result. We would never be able to do that. I'm sort of walking you through what's in my head with it. The model is ideal. So if you get a wrong result with an ideal model, you don't have a result. You can't do that, right? So the result of less than ideal is what you're left with. And the question is, what level of less than ideal do you want to be part of? The two-stage analysis, perhaps, where you do the prediction in a separate process, might be the way to end this. I did not add that here, but it could be a way around it where you get close to it and you're still better than what we showed yesterday. Like you're closer to the ideal than yesterday's model, but you're still avoiding the problems that we're seeing in this prediction simultaneously.
Would it make sense to treat all the measurement model parameters as calibrated, fix them to whatever you found in a previous model so that they can't even wiggle to reduce the complexity?
I don't think so.
Because I've seen that sort of logic be applied as well.
So here's the fun thing about Bayesian IRT. When you fix the measurement model parameters, the variance of theta shrinks. So you have more precision on theta than you actually think you do. Again, less than ideal, but I hesitate to do that. I think where I would go after this is a two-stage model from it. But I didn't show that to you. But,
You
yes.
mean output factor scores and do stuff?
Yeah, output the thetas, output the random intercepts, and do those analyses. Yep.
Okay, so output thetas and random intercepts and then use these as variables.
That's right.
The multi-level model we just saw yesterday.
That's right. Yeah, or not even multi-level, because those are the multi-level components. It would just be a straight regression analysis in that case. So what happens when you do that is the output, like if you look at the mean of the posterior distribution of the EAP estimates, and you look at the standard deviation of those EAPs, it's going to be shrunken from the standard deviation parameter we have here. That's the effect of shrinkage on the parameters we have. So it'll be a little less than ideal, but I still think it's closer to the ideal than otherwise.
Could you use 1 over the standard error as some kind of weight?
You could, or you
Something
could,
like
or you
that.
could do a sample of those output of thetas as plausible values.
To try and reintroduce that kind of variability?
That's right.
And when I use them, like when I extract the parameters and do linear regression, I use a point estimate.
You could. That's less than ideal, but start there, yes. The more ideal would be to use a sample of the estimates. Instead of the point estimate, take a random sample of, I don't know, 50. If we have a lot, computers work well. And then, if you think of the data, what it would look like, you have 50 samples for each school of their theta, and then you have your predictor for each school as well. And then you weight each of the 50 by 1 over 50. So like there's like a weight to the analysis as well. So it doesn't look like, so you don't actually have 50 times the schools you have. You have the sample size would be 62 in that case. But I'm going into a topic where I didn't describe much, so I'm probably saying things that are out in the weeds a little bit. But trying to, in the United States, we have an educational program called NAEP, and I think Tim's and PISA do this also, where they take the result and they're weighting it by, they don't give you 1 theta, they give you 5. And they call them plausible, and they teach you how to use those in a secondary analysis. It'd be something along those lines. But again, I'm sorry I don't have that this week. You can see we've gotten to Friday at 12:15 p.m. and I don't know that we would be able to squeeze that into this week very easily. But if you're in the ballpark of this, I think this is your ideal. I think it's attainable. I really feel like if I can figure out what the technical problem is and resolve that, I'll first of all feel much more knowledgeable about what's like sort of the Hamiltonian process in STAN. But second, I think the results are actually real and doable and all in one form.
I think the other part of this is that it's pessimistic in the sense that these are binary item responses. Like this is like the lowest information a variable can possibly have. And if you're dealing with ordinal or something that's more numeric, like there's more to work with, I feel like that has to go better. So maybe just wishful thinking.
Also a question, like the data I have is on a Likert scale, and I can like use this and just put my Likert scale data in. Like.
Yeah, so things would change. You could do the assumption of factor analysis, which we showed before, where the STAN code for the items themselves, let me grab that model. Your y would follow a normal distribution. That's the simplest way. I think we mentioned at the poster session last night, if you want to do something like a graded response model, STAN has a function called ordered categorical logit, which will build the multiple layers into, like the submodels, into it automatically. And if you wanted to use something like a nominal response model, there's an unordered categorical logit function as well too that somewhat simplifies it. But I would start with pretending they're continuous, even though that's less than ideal too, but just to get things working at first, and then from there, if you want to try to achieve the ideal, change. Good questions, so thank you. All good questions this week. All right, what have we lost? What did we not tell you that you want to know? Yes. No, this is great. This is great.
Well, I will have missing data.
Yes, and I will.
Oh boy.
Give me a moment. Let me do this.
I would love to have simpler data.
No, we all have missing data. Unless in this data, we wouldn't know it's missing was coded as wrong, which is also weird. On my website, I taught Bayesian psychometric modeling last year. And where did I do this? Here's a lecture on the missing data functions itself. So here, I have a bunch of Likert items. This is what Stan tells you if it's missing. But this lecture here will get you through the concept in Stan. Basically, we needed to come up with how many observed observation we had per item, and then which ones those were. And from there, it's the data block. The Stan, we would loop over. Oops, no. I don't have my Stan syntax segmented here, but here's the model block. We're looping over which items we had observed. And by the way, this is that graded response model. This is the function for it, ordered logistic for it. So there is, if you email me, I'll be happy to send you this link. And otherwise, if you have other code, I troubleshoot it for you if you'd like to. But this is basically what we're trying to do is basically have Stan skip over the outcomes that were the non-complete cases that we wouldn't be able to run the analysis for. Yes?
Now I'm also trying to implement a model in Stan in terms of missing data. What I use is to if function.
Yes, you can do that too.
Does it work?
That works just as fine. Yes,
Okay.
absolutely. Absolutely. Yeah. It's just if this value, do this. Yeah, indicators of observed or versus not. Yep. Yeah, I had tried to. The difference between that approach and this approach might be, Stan, is a little bit slower in yours, but it's only might be. The reason why is every iteration, it has to at least loop through everything, whereas this one I've tried to make it just go the vector of what's observed. But it's trivial. If you get it to run, it's good, and that works sufficiently, right? Yeah, running is the first thing, elegant code is the second, and elegant code that breaks is not useful. So very good. That works as well too. So there's other ways that you could do that as well. Yes?
Maybe this is a ignorant question, but is it common to impute data in these cases? Because I'm not familiar with this kind of data. So with this item, is it common?
Not usually, at least in the measurement models. And so the reason for it is if you don't impute, but you use the likelihood function that's full information, you make an assumption of your data that's something called missing at random, which is a step better than completely random. Now, and so skipping over data that's missing or not observed maintains that assumption. If you impute data, depending on how you impute the data, you might get that assumption, or you might not, right? You might buy the imputation process itself relies on a set of assumptions, some of which can't be tested. And if some of those are not true, then the data that you fill in may change a lot of results only because of what you've chosen for imputation. So in my personal work for psychometric data, if a student provides, maybe you have a 10-item survey and a student only give you 7 responses, I would just use the 7 they had and not impute the data that they gave you otherwise. That's my own personal thought, because the imputation could make things worse and I wouldn't know it potentially. But that's me. A lot of people will disagree about that, I think.
Not me.
Not you. All right. Any other questions? Congratulations, you made it. That's it. Should we call it a day? Call it a workshop?
Call it a week.
All right. Thank you for being here. I like it. I like it. So we have this afternoon, there's the final keynote address at 2 p.m., where the last keynote was 138, something like that. And then there's a farewell session after that. I think it sounds like it's just little drinks and hors d'oeuvres or whatever, coffee, snacks, stuff like that.
Oh, and the poster winners.
And the poster winners, yes. Well, first of all, can I just say your posters were excellent.
Yeah, there are no.
I came
winners
away
for
from.
this.
I'm serious. When I came away from that, let me do this because I don't want